Now we consider the WKB approximation. Consider a Schrodinger equation of the following form: minus h bar square by 2m d square psi by dx square plus v of x psi of x equals e times psi of x. Some of the situations where a Schrodinger equation of this kind appear are the following. If we have a particle of mass moving in a one-dimensional potential v of x, the corresponding Schrodinger equation is exactly given by this equation. And another situation where it can arise is a case of a particle moving in a three-dimensional spherically symmetric central potential denoted by, say, Vc of r. Since the potential is spherically symmetric, the Schrodinger equation can be separated in the spherical polar coordinates, and if we denote the radial component of the wave function, that is the component that depends only on the radial coordinate, by, say, r, l, r, where l can take values 0, 1, 2, 3, etc., corresponding to the angular momentum quantum number, or the number representing the spherical harmonics y, l, m, theta, phi. And we define a new function psi l as rl divided by the radial coordinate. Then this new function satisfies an equation of this form, with a new effective potential VL of R given by the sum of the central potential Vc of R plus the rotational kinetic energy given by h bar square times L into L plus 1 by 2m r square. This is something that we have already seen while solving the hydrogen atom Schrodinger equation in semester 2. Now our aim is to find a solution to this equation, the Schrodinger equation in one dimension, for example. To do so, we first rewrite this equation by making the following definition. We write k square of x as 2m times e minus v by h bar square. Then this equation simply becomes d square psi by dx square plus k square x times psi of x is equal to 0. Now, in the simple case where the potential v of x is independent of the position or independent of x, then k is a constant, and therefore we can write the solution in the following way. When E is greater than V, then this quantity is a positive number, and therefore k is a real number. Then the solution is given by a linear combination of exponential of minus ikx and exponential of ikx. Whereas on the other hand, if E is less than V, this quantity is negative, and k, which is square root of that quantity, will be an imaginary number. So if we define 2m by h bar square v minus e as k mod square, or say some, k mod square. Now the left hand side is now a positive number, so k mod can be written as plus or minus of square root of 2m v minus e by h bar square. Now this is a real number now, and the solution of, or the square root of 2m e minus v by h bar square can now be written as plus or minus I k bar. So replacing this k by plus or minus I k bar, we will get the following solution. Psi of x is equal to a linear combination of e to the power minus I k modulus x plus d times e to the power k modulus x. And this is the solution when e is less than v. And in the WKB method, we consider a situation where v now depends on the position, that is x variable, and we write a solution of the following form and a complex exponential. So we write psi of x as e to the power I by h bar times s of x, and this s of x has the dimensions of h bar now, and s by h bar now will have no dimensions. So once we make this substitution, this equation will now become an equation, a differential equation for s. To find that, we see that the second derivative of psi with respect to x can be written in the following form. By substituting for psi using this formula, take the second derivative, you will end up with this equation. And substituting this formula for d square psi by dx square in this equation, we end up with this equation. So ds by dx the whole square minus ih bar times d square s by dx square minus k square h bar square equals 0. Now remember, we are considering a situation where E is greater than V here, and therefore K square is a positive quantity, or in other words, K is a real number. Now to proceed further and make assumptions, we write S of x as a power series in H bar. And before doing that, let us see that k square h bar square is simply given by k square. K square is defined as square root of 2m e, is equal to 2m e minus v by h bar square, and therefore k square h bar square is this times h bar square, and therefore equal to 2m e minus v. So it is independent of h bar. Even though we have written it like k square times h bar square, this quantity is equal to 2m times e minus v. Now we write s of x as a power series in h bar. So we write as the zeroth order term in h bar as s0x, and then h bar times s1x plus h bar square times s2x, and so on. And in equation 8, that is this equation, we substitute this series expansion of s of x, and we will only consider terms that are of order h bar or less. So we will neglect all terms of order h bar square and higher order terms. Okay, so the first term will come from the zeroth order term. The zeroth order term will come from the following. So in ds by dx can now be written as ds0 by dx plus h bar times ds1 by dx plus higher order terms. Now the square of that is given by that. So expanding it, we will have ds0 by dx whole square plus 2h bar ds0 by dx times ds1 by dx plus the next term is order of h bar square or higher. Okay, so this is order of h bar square. Okay, so now d square s by dx square has already an h bar multiplying it, and therefore if I only want to keep terms up to order h bar, I only need to take d square s0 by dx square here. Now this term is already of order h to the power 0, that is, it is independent of h bar because it is equal to 2m times e minus v. So substituting for ds by dx by this, and d square s by dx square by ds0 by dx square, because this is already of order h bar, and if I take the next term, which is d square s1 by dx square, it has already an h bar there, so h bar times h bar becomes of the order of h bar square. So I only intend to keep or track terms that are up to order h bar, and therefore I will, for the time being, only write d square is 0 by dx square here. Okay, so now look at the zeroth order terms, or h to the power 0 terms coming from this equation. And in ds by dx the whole square, we have a term which is ds0 by dx the whole square, which is of the order of h to the power 0 because it does not depend upon h bar. So that is independent of h. And this term k square h bar square is also independent of h. And therefore, we can collect the zeroth order terms as ds0 by dx the whole square minus k square h bar square. Plus, next we consider terms of order h bar. So from this, we see that there is a term of order h bar, and that's given by 2 times ds0 by dx times ds1 by dx. And also this term ih bar times d square s0 by dx square, that is also of the order of h. So collecting those two terms, I have h bar times 2 ds0 by dx times ds1 by dx minus this factor I times d square s0 by dx square plus terms of order h bar square is equal to the right hand side, which is 0. Now we equate the coefficients of h to the power m on either side of this equation. The right hand side is identically 0, and therefore the coefficient of each power of h bar on the left hand side can be equated to 0. So equating first the coefficient of h to the power 0, we have this term equal to 0. So ds0 by dx square minus k square h bar square is equal to 0. Which means ds0 by dx is the square root of k square h bar square, which is equal to plus or minus h bar k. And this equation can be integrated to get s0x as plus or minus h bar times integral of kx up to some point x. Here we have placed a lower limit on the integration, and placing a lower limit actually corresponds to fixing the integration constant here. Now since we are considering E is greater than V in this region, K, which is square root of 2m E minus V by h bar square, the positive square root of 2m h bar square times E minus V, and this is a positive number. As E becomes equal to Vx, K tend to 0. Now the next step is in equating the coefficient of h bar to 0, because on the right hand side the coefficient of h bar is 0. It's identically 0 for all powers of h bar. So equating this term to 0, we get the following. So 2 times ds0 by dx times ds1 by dx is equal to I times d square s0 by dx square. So I can write the equation for S1 as the following. ds1 by dx is equal to I by 2 d square S0 by dx square divided by ds0 by dx. Now we have already found the expression for S0, and therefore I can substitute that on the right hand side and get an equation for ds1 by dx. Now S0 ds0 by dx was found to be plus or minus h bar k of x, h bar times k, and which implies d square S0 by dx square will be equal to plus or minus h bar dk by dx. Now substituting that over here, I will have I by 2, this constant terms, and for d square S0 by dx square, I have dk by dx as I got here. So plus or minus h bar dk by dx divided by ds0 by dx is plus or minus h bar k. So the sign factors and h bar factors go away, and I will end up with this equation I by 2k dk by dx. So ds1 is simply I by 2 dk by k, which can be integrated to get s1x is equal to I by 2 logarithm of kx. Now in this region, k of x is greater than 0, and therefore I can write logarithm of kx, it's well defined, plus an integration constant c. So we have got S0 and S1. The terms of order h bar to the power 0 and h bar to the power 1 in the series expansion of S. And if we assume that the terms that are of higher order in h bar can be neglected, then we can approximate psi of x, which is written as psi of x is equal to e to the power I by h bar s of x. Now I can write it as S0x plus h bar S1x plus all higher order terms, which we can now neglect. And if we do that, I have an approximation here. So approximately equal to this, provided the higher order terms of S can be neglected. So in that case, this becomes I S0 by h bar plus S1x, this form. Now I have the form for S0, which is either plus or minus. S0 is given by plus or minus h bar integral x dx dash kx dash, and also I have an expression for S1x given by this equation. I can substitute that over here, and I will get an approximation for psi of x. Now as we see, S0 has two possibilities: plus or minus of this integral. Now since the Schrodinger equation is a linear equation, and if it has say two solutions, a linear combination of that solution will also be a solution. And therefore, I have two possibilities for S0 here, which will lead to two possibilities of psi of x, and I can take the solution as the general solution as a linear combination of those two possibilities. That will also be a solution of the Schrodinger equation. So one will appear with S0 given by this plus sign, and the second one will appear with S0 having this negative sign. So doing that, I will have the general solution, the WKB solution, as a linear combination of I by h bar, so exponential of I by h bar S0x, then e to the power I S1x, as I have seen here. So substituting S0 as say plus or minus h bar integral x dx dash kx dash, I will have the first term with plus sign. I have e to the power I, h bar is gone from that. Okay, so yes, integral over dx dash kx dash up to x. So that comes with this plus sign. And the second term is e to the power I times s1x. Now s1x is I by 2 logarithm of k of x. So I times s1x is minus 1 by 2 of that. So that is e to the power minus half logarithm of k of x. But then that can be written as logarithm of k of x to the power minus 1 by 2, which is nothing but 1 by square root of kx. Now taking the exponential of that, exponential of logarithm of 1 by square root of kx is simply 1 by square root of kx. So the first part of the solution is a, which is a constant, times e to the power integral up to x of dx dash kx dash divided by square root of kx. And the second part will have this s0 term coming with a minus sign. So it is simply a constant b times this exponential term coming with a minus sign. So e to the power minus I integral dx dash kx dash up to x divided by square root of x. So this is the form of the asymptotic solution, the form of the WKB solution for a region where energy E is greater than V of x. Now we have to do a similar calculation for the region where E is less than Vx. If we look at this figure, in the region between x1 and x2, so that is this region, energy E is greater than V of x. But for x greater than x2, that is this region, and for x less than x1, energy is less than V of x. So in that case, this quantity k square, which is 2m by h bar square E minus V of x, will be negative and k become imaginary. Now we can proceed as before, and we will define k square is equal to 2m by h bar square E minus V, but E is less than V, and therefore this can be written as minus of 2m by h bar square V minus E, and this is a positive quantity. When I take the square root of this, so k can be written as square root of minus 1, which is I, so plus or minus I, then square root of this positive quantity, which I call as gamma. So gamma square is simply 2m by h bar square times V minus E. Now, as before, we can now write s of x as a power series in h bar, and proceeding as before, we will get s0x is equal to plus or minus I h bar integral of gamma x up to x. Similarly, s1x is equal to I by 2 logarithm of gamma x plus a constant. Now gamma x is positive here because that is defined to be positive square root of this quantity, 2m by h bar square times V minus E. As before, truncating at first order in h bar, we can write the WKB approximate solution in the following way. So I have a linear combination of two solutions. The first one is exponential integral of gamma x dash up to x divided by square root of gamma x plus b divided by, b is another constant defining the linear combination, square root of gamma x times e to the power minus of integral of gamma x dash up to x. Now we need to remember that this WKB solution as written here in equation 19 and in equation 16 are valid only if we can neglect the terms of order h bar square and higher order in the power series expansion of S in terms of h bar. So the validity of the WKB approximation depends on this factor. So we have, say, the first order factor, which is h bar s1, should have magnitude less than, say, the 0th order term, and the higher order terms have continuously, decreasing orders of magnitude, so that we can safely neglect them. So one primary requirement is that, the first order correction or first order term in the series expansion is much, much less than the absolute value of the second order term. Now we know that S0 was defined to be, absolute value of S0 will be something like this, say integral over h bar times integral up to x dx dash kx dash. Now kx dash is equal to 2m e minus p of x by h bar square, and I take the positive square root. Now we are in a region where E is greater than Vx, and therefore k of x is always greater than 0. And k of x is positive as well. And therefore this integral, provided we are restricting the integration region to a region where E is greater than V of x, where k of x is always greater than 0, we can see that this integral lead to a monotonically increasing function of x. So S0 is increasing with monotonically increasing with x. Okay. So now suppose say at some point, say h bar s1 is much less than s0, and it will remain so for other values of x, provided the rate of change of h bar s1 is less than the rate of change of s0. So that means the rate of change of s1 is ds1 by dx, because the term has, say, h bar also, h bar times ds1 by dx, and should be less than the rate of change of s0, which is ds0 by dx absolute value. So if this condition is satisfied, h bar s1 will always have a magnitude less than s0 in this region. So now we know that S0 is equal to S0 absolute value. S0 is something like, say, h bar integral x dx dash kx dash, and therefore ds0 by dx, so we have a plus or minus term here. So plus or minus h bar k of x and ds1 by dx is equal to, we go back, and is equal to I by 2k times dk by dx. So I 2k times dk by dx. Now that means this condition can be written in the following way. H bar ds1 by dx is h bar times, put an h bar over here and put an absolute value, and I will have, say, h bar by 2k dk by dx, and that should be less than ds0 by dx. ds0 by dx absolute value is plus or h bar times absolute value of k. So now removing this h bar from these two, I can write 1 by 2k dk by dx absolute value should be less than or equal to absolute value of k. So this condition gets translated to a condition in terms of k in the following way. Now we define a local wavelength lambda x as 2 pi by k at that point, k at x. And if I take this k here, it will become 1 by k times this, and this will become 1. Okay, so that is what I have written over here. Now, so there is there is another factor coming up here. So you have a 2 factor here, and there is an 1 by k here, and from this you can see that 1 by k can be written as 2 pi, lambda by 2 pi. So this 1 by k, this k coming to the left becomes 1 by k, and that can be written as lambda by 2 pi, and this 2 coming here will make it lambda by 4 pi. So this condition can be equivalently written as 1 by absolute value of k times absolute value of dk by dx times lambda by 4 pi is much smaller than 1. And therefore, WKB approximation is valid provided this condition can be met. Now, what is the significance of this? dk by dx defines the rate at which k changes with x variable. And lambda is a wavelength, so lambda by 4 pi is a length. So dk by dx times this much length is the variation of k over a length lambda by 2 pi. The change in k over a length lambda by 2 pi. And we are dividing it by absolute value of k. So it is a fractional change of k over a length lambda by 4 pi, and that should be less than 1. So that means for the WKB approximation to be valid, the variation of k with x should be very small. And over a length of lambda by 4 pi, the variation divided by the value of k should be much smaller than unity. So when this condition is not met, then WKB approximation become a not so good one. So if we look at a particular situation where this approximation is not valid, we can look at the following case. Suppose k becomes 0. So as k becomes very small, k is appearing in the denominator, and dk by dx is a rate. So some finite rate. Dk by dx is finite, and as k becomes very small, this quantity becomes very large. And therefore this condition will no longer be met, and in that case we will not be able to use the WKB wave function to approximate the actual wave function of the problem. So k becomes 0 when So the definition of K is square root of 2m E minus V by h bar square, and K becomes 0 when E becomes V. So K tend to 0 as E tend to V. So the points where E equal to V are actually the classical turning points of the problem. So suppose we have a potential given by this form. This is V of x, and say this is equal to energy. And the difference between these two lines is equal to E minus V, and that is going to be the kinetic energy of the particle. Now, suppose if a particle is moving from this point toward this region, and we see that as it approaches this V of x line, E minus V is decreasing, and therefore kinetic energy is becoming smaller and smaller. And in fact, at this particular point, E is exactly equal to V of x, and at that point, kinetic energy is 0. Now the force on it is given by the negative gradient of the potential, and here the gradient of the potential is positive, and therefore negative gradient is negative. So the force is directed in this direction. So at this point, the particle has 0 kinetic energy, that means it has 0 velocity, and the force is in this direction, so it will turn back and move towards x is equal to 0. So that's why it is called a turning point. The same thing happens over here. The kinetic energy is 0 at this point, the point where V of x becomes equal to E, and the gradient of the potential is positive here, so negative here, and therefore the force is negative gradient, which is positive, and therefore the particle will turn back and move towards origin again. So these 2 points at which energy is equal to the potential are called the classical turning points. And near the classical turning points, E is very close to V, and therefore K is close to 0. And therefore we see that in this region, WKB solution not valid. Now to solve the Schrodinger equation, we need a single function that is valid throughout the allowed values of x. And the wave function should be continuous and differentiable as well, since the potential has no discontinuities and singularities over here. So that means since WKB solution is not valid in a region around a turning point, we need to find the solution in this region by an alternate method, and we have to match the solution with the WKB solution at the boundaries where they meet, so that we will end up with a continuously varying wave function psi of x. So our next task is to find a solution, a correct solution in regions around the turning points, classical turning points. So by the way, the WKB solutions are also termed asymptotic solutions. That is because they are valid only when they are far away from the turning points, so that K is no longer close to 0, and K will be varying sufficiently slowly so that this condition that we have written here is satisfied. So we call them asymptotic solutions. Now we look at the 2 kinds of turning points separately and try to find the solutions by alternate methods in that region, and then match the solutions obtained thus with the WKB solutions at the boundaries. Now we consider a solution at a turning point like this. So here this blue line corresponds to the potential energy curve, and the dashed red line corresponds to the value of energy. So E is equal to Vx at this point at x2, and therefore this is a turning point. Now we consider a region, by the way, here to the right of this turning point x2, the potential is larger than the energy, and to the left the potential is less than the energy. So we say that we have a barrier to the right of the turning point, potential barrier to the right of the turning point. Now we consider a region around the turning point x2 from say xl to xr, in which region v of x is almost linear, so that we can write v of x by a linear approximation, say v at x2 plus k times x minus x2, where k is the gradient of the potential at x2. Here it is positive, so k is a positive number, dv by dx at x2. Now the Schrodinger equation with this form of the potential becomes this, because now I can write say d square psi by dx square plus 2m by h bar square e minus v, but v is given by this v of x2, then plus k of x, k times x minus x2, so that is minus k x minus x2. But as we have seen over here, v of x2 is equal to e, and therefore this term goes away, and we will end up with minus 2mk by h bar square times x minus x2, exactly this term over there. So the Schrodinger equation with this approximation for v of x becomes this d square psi by dx square minus 2mk by h bar square times x minus x2 times psi is equal to 0. Now we make a variable transformation. We will first write a new variable x minus x2 and scale it by a number alpha, a term alpha. And we choose alpha cube to be equal to 2mk by h bar square. The reason why we choose this factor is because it simplifies this equation into the following form. But first let's go through it step by step. So once we have defined a new variable, which is x minus x2, rescaled by a factor alpha, which has dimensions of inverse length, inverse x for that matter. So then psi at a particular point x is defined to be equal to the function z at the corresponding z. For an x, there is an z, and psi at that point is written by a function z of z, where z is simply alpha x minus x2. So we may write psi of x is equal to z alpha x minus x2. Okay. Now d square by dx square in terms of z is given by alpha square times d square by dz square, and substitute that over here in this equation and choose alpha cube to be equal to 2mk by h bar square, and we get this equation. d square z by dz square minus z times c is equal to 0. And this is a standard equation called the Airy equation, and it has linearly independent solutions given by aiz and biz. They're called the Airy functions of the first and second kinds. This is Airy function of first kind, and this is Airy function of second kind. Since it's a linear equation, the general solution is a linear combination of the two linearly independent solutions. Now, the Airy functions have the following asymptotic forms. When z is much larger than 0 for large positive values, aiz has the following form, and biz has this form. For large negative values, aiz goes like this, and biz goes like this. So now the wave functions psi of x are written as a times the Airy function z plus b times biz, and in terms of x and y, so in terms of x we can write it in the following way: ai z is given by alpha times alpha times x minus x2 plus b, then bi times alpha x minus x2. Okay, so now that we have found an appropriate solution for the Schrodinger equation in the region around the turning point, we need to match this solution with the WKB solution at the boundaries where both the solutions become valid. So that corresponds to finding the boundary conditions, boundary matching between these two solutions, so that we will get a single continuous wave function. And this requires certain assumptions. The first one is that these 2 points xl and xr are far away from the turning point, so that at this point the WKB solution is valid. That's here. As we move from the left towards XL, WKB solution is still valid. And as we have seen earlier, this would be valid only when we are far away from the turning point, so that k is no longer very small and the variation of k with x is sufficiently small that the condition for the validity of the WKB solution is now satisfied. And together with that, we also assume that the solution in terms of the linear approximation of the potential is valid at this point. So on the one hand, we require that XL is far from X2, so that WKB solution is still valid as X goes towards XL, so that it is far from X2. And even though it is far from X2, XL is far from X2, and throughout this region, the solution in terms of the Airy functions obtained from the approximation of the linear approximation of the potential by this equation is still valid. So provided these two are valid, in this region we have a solution in terms of Airy function, and in this region we have the WKB solution. Further, since XL is far from X2, the variable z that we have defined as alpha times x minus x2, and here in this region, as we to the left of x2, x minus x2 is negative, and we assume that xl is far away from x2, and so that this quantity has a magnitude which is large. So we can approximate the Airy functions by the asymptotic form for large negative values. Okay, so now we have two solutions for this point. One is obtained by finding the asymptotic form of the solution in terms of the Airy functions for large negative values of this quantity z, and the other one is the WKB solution as x tends towards xl, and these two solutions should match at this point xl, so that we will have a continuous function psi of x. So now to the left of xl, we have energy E greater than V of x, and the WKB solution in that region is given by this form. Okay, so the situation that we are considering is this. So this is the point x2, and this is the point xl, and this is the point xr. Now we are considering this region, which is to the left of xl, and where we can approximate it by a WKB solution, because it is far away from x2. So the solution is given by the first factor is going to be exponential I, and integral from say dx dash kx dash up to x divided by square root of kx. Now we can change this limit. So we can in fact put a limit, let me put it as a x2 over here, because in this region from say some x over here to x2, E is still greater than V, and therefore in that region k is greater than 0 and it is real, and this particular form of since E is greater than Vx, this particular form of the WKB solution is valid. Now if I interchange these two limits, that is I make this x and this x2, I have to put a negative sign over here. And I have another solution also that comes with a negative sign in the exponent. So that will be e to the power I integral from say x2 dx dash kx dash divided by square root of kx, and there will be corresponding coefficients defining the linear combination of these two. So I'll put a coefficient a there and a coefficient b here, and I will get this equation. Psi kb, that's WKB solution, is given by this linear combination of the two solutions. Now if you look at it carefully, you see that I have put a limit here, x2. So that simply redefines this constant a. Also, I have chosen a convention in writing the integrals in the exponent in the following way. The upper limit is taken to be the larger value of x, and the lower limit is taken to be the lower value of x. Here x is smaller than x2, and therefore I have taken the integral to go from x to x2 in both these exponentials. And this is a convention I will be using throughout these lectures. Now, as x moves towards xl, that is, I move towards this point, and remember, this is the region where I can approximate Vx by the linear form. So as x move towards xl, the integration region is from x2 to, from x to x2, and as x move towards xl, this becomes almost the region between xl and x2, where the linear approximation of Vx have been used in arriving at the solution in terms of the Airy functions. So here also we can use the linear approximation of V of x. Then the expression for k of x, which is given by square root of 2m by h bar square times e minus v, now simply becomes this. Now there is a minus sign over here, but now looking at this, x is less than x2, and therefore x minus x2 is negative. So I can absorb this minus sign inside here and write it as x2 minus x. And now 2mk by h bar square was defined to be alpha to the power 3, and therefore I will get k of x as alpha to the power 3 by 2, x2 minus x, that is, absorbing this minus sign, this becomes x2 minus x to the power half. So k of x has now a simple nice expression. So the integral of k of x over here can be explicitly done, and I will get the result to be approximately equal to this. It is approximate because of the approximation that we have made here for k of x. And substituting that form of the integral, the WKB solution as x move towards xl becomes this. And further, on the right side of xl, we have a solution in terms of the Airy functions. Now its argument is x minus x2 times alpha, but x minus x2 is negative here and it is far away from x2, and therefore the argument of the Airy functions are all large negative values, and therefore we can use the asymptotic expression corresponding to large negative values of the argument for the Airy functions. And we had written this down earlier, and substituting that over there as x tend to xl, the solution in terms of the Airy functions will become this. We just need to substitute for z there in the asymptotic form for large negative values of aiz and biz. Now these terms small a and small b are the linear the coefficients defining the linear combination of the two linearly independent Airy functions. Now this solution as x tend to xl should match with this solution, WKB solution as x tend to xl. We can compare this with this, but then this is in terms of complex exponentials, but this is written in terms of sine and cosine, but we can convert this into complex exponentials using the formula sine of x is equal to e to the power ix plus e to the power minus e to the power minus ix divided by 2i, and cosine of x is equal to e to the power ix plus e to the power minus ix divided by 2. And doing that, we will end up with this equation. So sine is replaced by that and cosine is replaced by that, and there will be terms of e to the power I 2 by 3 then this factor plus pi by 4 coming from both these terms, and collecting them together I will have the coefficient of this term involving this factor and IB plus BA. And here in this term I will have IB minus A. So now this can be directly compared with this equation 32. Look at this term and look at its coefficient, look at the corresponding term over here. And these coefficients should match. And similarly, the coefficient of this term here and this term over here should match. And matching them, we have two equations. A equal to this and B equal to this. So now we have got a relationship between the coefficients defining the linear combination of the exponential terms in the WKB solution and A and B that defines the linear combination of Airy functions to the right of XL. Now we have to do a similar boundary matching at XR to the right side of the turning point X2. Now to the right side of X2, the WKB solution is given by this form because their energy is less than V. So V of X is greater than E. So we have to write the solution in terms of gammas. Again, we assume that X of R, XR is far away from X2, so that to the right side of X of R, we have the WKB solution valid, and to the left side, we have the solution in terms of Airy functions valid. Now, since XR is far away from X2, we can make the asymptotic approximation for the Airy functions. Now, X minus X2 is positive to the right side of X2, and therefore the argument of the Airy functions there is large positive values, and therefore if you want to use the asymptotic expressions for the Airy functions there as X tend towards XR, we should use the expressions corresponding to the asymptotic expressions corresponding to large positive values of the Airy functions. And similarly, on the right side of XR, we use the WKB solution, but as X tend towards XR, now in the integration that we have defined over here, it is from X2 to X. Now here X is larger than X2, and that's why we have defined the integral in this way. And in that region, as X tend to XR, the integration region is from X2 to some X which is close to XR, and in this region the linear approximation of V of X is assumed to be valid. So again, just as we done before, we can write V of X by its linear approximation, and then we get an approximation for gamma X, which is alpha 3 to the power alpha to the power 3 by 2 times X minus X2 to the power half. Then I can do the integral in the WKB approximation. So that's given by 2 by 3 times alpha X minus X2 to the power 3 by 2. Substituting that here in this equation, as X tend to XR, the WKB solution can be written in this form. As we have done before, now we have to match this solution with the solution in terms of the Airy functions as X tend to XR. There we use the asymptotic expression for Airy functions for large positive values of its argument. And if you do that, we get this equation. And at X equal to XR, this solution should match with WKB solution. So the factors you can see here, you have an exponential factor 2 by 3 alpha X minus X2 to the power 3 by 2, and I have the same factor over here. Similarly, corresponding to this, I have this term over here, and their coefficients should match. And this would require that a, that small a, is equal to, this term 2 times square root of pi by alpha times d, and b is equal to this. Then from the boundary matching at XL, we have two equations. A is equal to this combination and B is equal to this combination. And now from boundary matching at XR, we have A given by this and B given by this. Substituting these two values here, we will get A equal to this and B equal to this. Okay, so we now have an expression for A in terms of C and D, where C and D are the coefficients defining the linear combination of the WKB solutions to the right side of the turning point, and A and B are the corresponding coefficients defining WKB solution to the left side of the turning point. So we now have connected the coefficients defining the WKB solutions to the right side of the turning point to those on the left side of the turning point. Now using this form, the WKB solution for x values less than XL is given by this form, where I have replaced A by this form and B by this term. Okay. So collecting together factors of the complex exponentials, we can write it in terms of the cosine and sine terms. So psi for x less than XL have this form. Whereas the asymptotic solution, WKB solution to the right of the turning point for x greater than XR is given by this. Now suppose on the right hand side D is equal to 0. Okay, then the solution on the left hand side is simply given by the first term. That is because D is 0 there. So that means this term corresponding to the WKB solution on the right side of the turning point continuously connects to this term corresponding to the solution on the left side. And similarly, this term corresponding to the solution on the right side of the turning point connects continuously to this term corresponding to the solution on the left side of the turning point. Okay, so symbolically, we so this connection is called the connection formula, and we write it in the following form. If we have a turning point of this type where we have a potential barrier to the right side of the turning point, the solution e to the power integral from x2 to x dx dash gamma x dash by square root of gamma x connects continuously to this term. And similarly, the corresponding solution to the right side with this negative exponential connects to this sine term on the left. They are the asymptotic connection formulae, because they connect the asymptotic WKB solutions on either side of the turning point. Now we can do a similar analysis for a turning point like this, where the potential barrier is to the left side of the turning point. In that case, the formula is like this. So on the left side of the turning point, we have V greater than E, and therefore the solution will be this exponentially decaying solutions, which are given by e to the power x integral of gamma x from x to x1 divided by gamma x, and that term gets connected to the cosine term on the right side. And similarly, this term with negative exponential gets connected to the sine term on the right hand side. And there is an alternative way of writing these connection formulas, because this cosine factor with this pi by 4 can also be written in the following way. See, sine x plus pi by 4 is actually cosine x minus pi by 4, and cosine x plus pi by 4 is minus sine x pi by 4, x minus pi by 4. And using this over there, we can rewrite the asymptotic connection formula in the following way. So if we have a potential barrier to the right side of the turning point, then the solutions of this form get continuously connected to the solution sine terms with, instead of plus pi by 4 in the earlier case, I have a minus pi by 4 over here. And similarly, this solution to the right side of the turning point gets continuously connected to this term. Now, if the barrier is to the left, we have a turning point like this, and in that case also a connection is similar to that, but then I have this exponential factor, continuously connecting to the sine factor over there, and similarly this negative exponential factor connecting continuously to the cosine factor over there. So these are the asymptotic connection formula for the WKB solutions to the problem.